Good afternoon, everyone. I welcome you to the last session of the research seminar we have today. So first, I will introduce the speaker. First, Chundu Tamang. She's the PhD candidate under Simple Hub at the center, and also she's working under Alan Manalo, Polly, and Tristan. And her research interests include sustainable development and waste management and green building designs. So now the floor is for you, Chindu.
Okay, am I audible? Hello? Sound is coming out of mine. Sorry, I've run teething problems. Yeah. Yeah, so I think everyone can hear well. Okay, so thank you very much, Prateep. I'll get started and share my screen first. Okay. Hello everyone. Thank you very much for your presence today. My name is Chundu Gyem Tamang, and the topic of our research project is reprocessing waste polyamide for sustainable saccharode guides. My supervisors are Professor Alan, Dr. Wahid, Dr. Tristan, and Professor Polly. And we also have our industry partner, Oil Fill Piping System. So I'll start with the introduction. So according to the National Waste Report 2022 of Australia, total waste of 75.8 million tons was generated, from which it had a disposal rate of 37% and a recovery rate of 63%. However, within these records, the lowest recovery rate was for polymeric waste, with 87% of the total waste being sent to landfill. And when we talk about polymeric waste, 50% of the total polymeric waste generation was from the commercial and industrial stream. And regarding the commercial and industrial sector, we also need to take into account the waste generation from the petroleum or the oil and gas industries. So hence, if we look at the waste, different waste categories from the oil and gas industry, so polymeric waste constituted 11% of the total waste. And while the recovery rates for the other waste categories, such as masonry materials, metals, paper and cardboard, glass, and other waste were really high at 91, 90, 67, 62, and 66% respectively. It was once again the polymeric waste which had the lowest recovery rate at 23%, with 77% being landfill. So therefore, we also need to consider the waste generated from the disposal of thermoplastics from this industry. For example, 300 metric tons of waste is being generated from the disposal of rod guides just by our industry partner Oil Fill Piping System in 1 year. So now to give you a better understanding of what saccharode guides are and what their application is, so this image here represents a typical saccharode pumping system, and it also shows a section of the downhole. So this is known as the tubing, and these is the saccharods. So saccharods are actually joined to one another, so through the joint in the coupling. So there is a string of saccharods, and it is known as saccharode string. And this component right here is known as the saccharode guide. So this saccharode guide is essentially in between the tubing and the saccharode. Now on its application, while there are different types of artificial lift systems such as the electrical submersible pumps, the PCP pumps, hydraulic pumps, and gas lift systems, the rod pumping system is the most abundantly used artificial lift systems around the world, representing 85% of the total system. So this is where the rod guides are used as a downhole component. And there are different and various types of guides and different types like designs of the rod guides. However, in general, there are two major types of rod guides, which are the filled installable and the mold-on guides. So in this project, we are focusing on the mold-on guides. And with respect to the guide material, we are working on polyamide 6, which is nylon 6 with 25% glass fiber reinforcement. And these guides are exposed to downhole operating temperatures of 70 to 100 degrees Celsius and weigh about 150 to 300 grams each. Moving on to the actual application of rod guides. So in a sucker rod pumping system, we can either have the system failure or the equipment failure. So the three different types of equipment failure, which are like the tubing failure, the sucker rod string failure, and the downhole pump failure, are failures related to the inefficiency or the lack of rod guides, which causes 50 to 85% of the total well maintenance cost due to the sucker rod or tubing wear. And this in turn also leads to well downtime and production loss, and also the expensive equipment replacement costs. Now, on how the rod guides can actually prevent these different types of failures, firstly, it provides the rod string centralization and the prevention of rod buckling. So if you take a look at the image here, during the downstroking movement, due to compressive forces and pressure differential, the rod string can buckle. And if you can see here, it can lead to the contact between the sucker rod string and the tubing. Okay, so what the sucker rod guides can actually do is the installation of rod guides at regular intervals can actually centralize the rod string, which can prevent the rod buckling. And the problems associated with the rod or coupling to tubing contact is firstly the tubing failure, which takes place especially in deviated wells, in which the coupling can slap the tubing at an angle, which causes the formation of holes in the tubing. And it can also lead to other different types of mechanical failures of the tubing. Additionally, the metal-to-metal contact can cause sucker rod failures, which in turn can lead to increased corrosion. So rod guides can essentially provide corrosion resistance as well. And while it is not very prevalent in Australia, rod guides are also used for paraffin control through their scraping action. So hence, in summary, the use of rod guides actually leads to improved pumping efficiency through reduced buckling, reduced surface contact, reduced corrosion, paraffin, and all of these actually leads to a reduction in equipment failures, well downtime, production delay, and replacement costs. So since sucker rod guides are such important downhole components, some operators use 3 to 4 guides per rod, while others may use as many as 10 guides per rod, according to the well requirements. So if we consider each sucker rod of 25 feet, and if we are taking an example of an average 8,000 feet deep well, we are looking at 320 rods per well, which translates to 1,280 guides per well, if just 4 guides per rod is used. Likewise, our industry partner oilfield piping system has supplied 120,000 guides in the last 2 years. And considering the different downhole material suppliers across Australia, we are looking at a total of, we are looking at a total of, sorry, I had a glitch there, a total of approximately 600,000 rod guides. Since we are focusing on polyamide 6, such high consumption is a big cause of concern, since the recycling rate of polyamide in 2019 was just 2%, while 98% of the polyamide production was resulting from the exploitation of new resources. And polyamide 6 in particular constitutes 2/3 of total polyamide production. Moving on to the environmental impacts of polyamide 6, we need to consider both the pros and the cons. So the advantages are that it is durable, it is long lasting, it has high strength, good abrasion and wear resistance, good thermal properties. And the main property which makes it a good material to be used as a rod guide is its excellent fuel and oil resistance. So this makes polyamide 6 a perfect material to be recycled. However, there are also some disadvantages of polyamide 6. So one is that its production has a very high resource consumption. So if you look at the table here, a total of 120.47 megajoules of energy is required to produce just 1 kg of polyamide 6. And it also has a high greenhouse gas emission, which includes nitrous oxide, which is like 300 times more dangerous than carbon dioxide. And as additionally mentioned by in the previous presentation by the previous presenter, Polyamide 6 is also highly combustible and it can catch fire easily, resulting in hazardous smoke containing nitrous oxide, hydrogen cyanide, and dioxins. And also, the polyamide 6 has high carbon footprint. So since polyamide 6 has such significant environmental problems, we should try to follow the waste management hierarchy system where prevention is the most preferred and disposal should be the last alternative. However, in current practice, what is happening is 100% of the high value rod guides are being disposed in landfill. And with this project, we are trying to propose a new technological process of recycling the rod guides. So therefore, in order to prevent and recycle, it is important to firstly understand the failure of rod guides. So this picture here shows you a molded on rod guide, and this section is known as the erodible wear volume. So if you look at the image here, so this is the tubing, this is the coupling, this is the rod, and this section of polymeric section of the rod guide is known as the erodible wear volume. So erodible wear volume is the part of rod guides which prevents the metal-to-metal contact between the sucker rod or coupling with the tubing. And the existing literature studies on rod guides are solely focused on the concept of erodible wear volume only in order to increase its service life. However, still then in current practice, what is happening is the operators replace the rod guides just based off prediction that it has lost a significant amount of its erodible wear volume without actual site inspection. So if we want to reproduce a proper recycling technology, it is very important to determine the other causes of failure so that we can evaluate its recyclability. Hence, to determine the other causes of failure, we will have to determine firstly the chemical property changes due to the exposure to different downhole contaminants. Secondly, we'll have to look at the physical degradation through the physical and microstructural property change evaluation. And finally, we have to determine the thermal property changes due to the material's continuous exposure to high temperatures in the downhole environment. For example, during its operation in the downhole environment, the rod guides are exposed to various types of contaminants. It undergoes physical degradation due to the frictional forces and the stroking movement, and it is also continuously exposed to the high temperature. So what the operators do is, in order to make sure that the wear of the rod guide is not just one-sided, but it is evenly distributed, they often use rod rotators. But the effect of using rod rotators is usually the best at the top section. However, in the midsection, the wear starts becoming uneven, and it is at the bottommost section is where the rods are like severely worn, they are broken, they are missing parts and mechanically damaged. And also the lowest one-third section of the well is also the one which has like the most aggressive solids with higher specific gravity, higher chemical and higher heat exposure. So therefore, it becomes necessary to evaluate the properties of the rod guides and their failure mechanisms according to their location of installation so that we can generate specific location-based data collection and analysis. Now we have conducted a few preliminary characterization tests on 5 numbers of randomly collected the rod guides from our industry partner, but I need to stress here that we do not have information on the exact location of installation of these guides because they were just collected. So firstly, for the FTIR, 5 different contaminated samples and 2 neat samples were tested and compared to determine the unknown materials and the surface contamination. So all the peak wave numbers of the IR spectra represented the major functional groups constituting polyamide 6 and were identical for all the samples, including both neat and contaminated, as per the assignment of the IR bands reported previously in literature. Secondly, for the scanning electron microscopy test, firstly, the neat guide samples were seen to possess continuous, flat, smooth, and clean surface with fewer irregularities, which indicated homogeneous and good quality morphological properties. But it was the used guides which were found to have significant changes in the morphological properties, and it exhibited increased degree and rate of surface degradation in the form of like there were cavernous structures and also impurities, which was embedded sand and silt, along with very irregular surface and complete loss of smoothness and flatness. There were also some wear and tear, which was represented by breaches, fractures, voids, and cracks. And in the contaminated or the used samples, we could also see the exposed glass fiber reinforcement, which was protruding from the polymer matrix. Finally, in the DSC test, a total of 6 samples were tested, and the average melting temperature recorded was 222.16 degrees Celsius. And the minimum melting temperature recorded was 222.16 degrees Celsius. The maximum melting temperature recorded was 223.69 degrees Celsius, with the average melting temperature of 222.95, which was pretty consistent for both the used and the neat samples. So again, these were just the preparatory tests and results, and the guides collected were not sorted according to their location of installation. So these results are not very comprehensive. Moving on to the research gap and objectives. So broadly, there are 2 specific research gaps. The first one is that there have been no studies till date conducted to evaluate the recyclability of used rod guides, apart from its acknowledgement as an important downhole component. And also a few studies have been conducted to determine the erodible wear volume of used rod guides, the wear rate, in order to increase its service life. Secondly, even regarding polyamide 6 recycling, while there are like abundant researches on different types of polymers such as polyester and polyolefin, owing to their large volume, the waste volume. So recycling studies on polyamide 6 is currently limited, and the few recycling studies that we do have is focused on the polyamide 6 from automobile and textile industry. So when we are considering polyamide 6, which has been exposed to the aggressive downhole environments in the oil and gas industry, it has never been studied till date. So due to the lack of the characterization studies, we do not have information on the impact of location, and we also do not have data on the effective decontamination processes, and we lack the scientific research on determining the recyclability of rod guides based on the determination of optimal mix ratio, in which we can incorporate the used guide material and use it as a feedstock in manufacturing new guides, and also do the technical performance evaluation of the new novel rod guides, and finally generate scientific evidence-based data on the effects of recycling polyamide 6 from the oil and gas industries. So therefore, in order to address these gaps, we have 4 different objectives. So the first objective is to experimentally evaluate the changes in chemical, microstructural, and thermal properties of used polyamide 6 guides through the characterization test, and subsequently compare the change in characteristic guide properties according to their location of installation, more specifically from the top and bottom of the well, but we'll also be evaluating the changes in the properties from guides collected from the midsection of the well. Number 2 is to determine the decontamination processes according to the characterization results. Number 3, to experimentally establish the optimal mix design for waste polyamide guide material to be used as feedstock through mix proportioning with virgin polyamide. And finally, to determine the physical, mechanical, rheological, thermal, and chemical properties of the new novel rod guides through laboratory and field testing for targeted industrial application. So the method employed in the study design will consist of laboratory and field experiments. So this is the proposed pathway in which we will be converting the waste rod guides into sustainable rod guides through the process of collection, characterization, optimized mix design, and performance evaluation. And this is the outline of the methodology, which will consist of literature review in the text study, and for lab experiments, we will have 3 separate but interlinked studies. And then finally, we have field testing for the end-use application. So I'll briefly run you through the materials and methods under methodology. So these are the different types of guides that we have included in this study. So the guides are made of polyamide with glass fiber reinforcement, and the guides are designed with slanting vanes, and they're also pigmented. And under method, so this is the method. So if you look at the proposed experimental method, we will have virgin polyamide 6 and waste polyamide 6 denoted by PAV and PAW. So the waste or the used polyamide 6 will be subjected to characterization, and based on the results of characterization, we will also implement the effective decontamination process prior to the formation of optimal mix design. Then the decontaminated or treated material will undergo granulation. And the used polyamide material from the rod guides will also be subjected to drying processes as required, because weight processing of polyamide can cause hydrolytic chain station and the molecular weight reduction. So these treated waste material will be mixed with virgin polyamide pellets in the combination of 0, 30, 50, 70, and 100% by weight. And through the performance evaluation tests of the resulting guides, the material, we will devise X percentage of waste material to be added to Y percentage of virgin material. So that will be the proposed novel guide composition. So contribution to the field of research. So through this research study, so we will be working on changing the post-service pathway of used rod guides. So in current practice, what's happening is the rod guides are simply collected, they are shredded, and they are being sent to landfill. So now we will be proposing a new alternative circular cycle of recycling the rod guides, which will consist of the steps of collecting, sorting it, treating it, pelletizing, and processing it. So it will be a circular cycle, ongoing cycle. And then this will lead to a more greener or sustainable approach. So we will come up with new novel rod guides through the processes of decontamination and recycling, contributing to sustainability and circular economy in the oil and gas industry. And my references. Thank you.